Hello friends, grab your coffee, grab your cookie, and maybe clean some lint off your shirt, because today we are talking about textile dust. Yes, the dust made of tiny fibers that somehow covers every surface, floats forever, clings to your clothes, and makes your entire facility look like it is permanently shedding sweaters. My name is Klepik, and for 15 years I have been designing dust and lint control systems for textile mills, spinning operations, weaving plants, non-woven production, cutting rooms, and garment factories. Let me break down what textile dust really is and how we handle it safely and efficiently. What textile dust really is. Technical description. Textile dust is a mix of fibers, microfibers, yarn fragments, lint, and filler particles generated during textile manufacturing. Its technical characteristics. First, particle sizes range widely from 1 micron to several millimeters. The most airborne fraction is from 1 to 50 microns. Second, bulk density is extremely low, usually between 10 and 60 kilograms per cubic meter. Third, airborne concentrations can rise from a few hundred to 20,000 milligrams per cubic meter in cutting, spinning, and carding rooms. Fourth, fibers can be natural, synthetic, or blended, each with different behavior. Fifth, textile dust is highly airborne and remains suspended for long periods. This combination makes textile dust one of the most persistent and difficult to control industrial dusts. Types of textile dust: natural, synthetic, blended. Different textiles produce very different dust patterns. Natural fibers: cotton, wool, linen, hemp. First, they shed fine cellulose fibers. Second, cotton dust is known for respiratory hazards. Third, natural fibers create soft, fluffy airborne clouds. Synthetic fibers: polyester, nylon, acrylic, rayon. First, they generate microplastic particles. Second, some synthetics hold strong static charge. Third, fibers may be sharper and more abrasive. Blended fabrics, alloys of natural and synthetic fibers. First, dust contains mixed fiber properties. Second, behavior varies depending on the ratio. Third, often more airborne due to lightweight microfibers. Understanding fiber type is essential for choosing the right filtration system. Why textile dust is dangerous. Textile dust introduces several hazards. First, fine fibers irritate the lungs and can cause chronic respiratory issues. Second, cotton dust is associated with a condition known as bisonosis, sometimes called brown lung. Third, synthetic microfibers can accumulate deep in the respiratory system. Fourth, textile dust is combustible under the right conditions. Fifth, buildup on motors and electrical panels increases fire risk. Sixth, fibers wrap around moving equipment, causing overheating and malfunctions. In high production environments, dust can also reduce visibility and contaminate products. Physical behavior of textile dust and airflow. From an engineering perspective, textile dust behaves uniquely. First, it is extremely light and remains airborne for long periods. Second, it forms floating clouds that travel far from the source. Third, fibers tangle and create mats inside ducts and filters. Fourth, some fibers hold strong static charge. Fifth, microfibers behave like smoke and require high-efficiency filtration. Because of this, I designed duct velocities from 4,500 to 5,500 feet per minute, higher than many other dust types. What filtration equipment works best? Choosing the right equipment depends on the type of textile process. For fine airborne fibers and microdust, I often use a faux EHN cartridge collector. First, it captures fine particles and microfibers efficiently. Second, it offers large filtration area for continuous operation. Third, membrane-coated media helps prevent fiber embedding. For heavy lint and fluff loads, a Baghouse blizzard is often more suitable. First, it tolerates large fiber volumes without clogging. Second, it handles long, irregular, and tangled fibers well. Third, it maintains high airflow even with heavy lint load. For combustible textile dust, safety features must include: first, explosion vent panels sized for the collector. Second, anti-static filter media for synthetic fibers. Third, grounding and bonding across the system. Fourth, isolation valves in ducts to stop flame propagation. Fifth, optional spark detection for high-friction machines. Capture hood design for textile machinery. Source capture is essential because textile dust spreads quickly. Effective methods include: first, multi-point extraction on spinning frames. Second, enclosed hoods for cutting tables and trimming stations. Third, overhead canopy hoods for carding and combing machines. Fourth, direct pickup points inside edge trimmers and sewing lines. Fifth, enclosed conveyors for fiber transport. Proper capture significantly reduces airborne lint and improves air quality. The most common mistakes I see with textile dust across textile facilities, I repeatedly see these issues. First, using duct velocities that are too low for lightweight fibers. Second, installing filter media not designed for lint and microfibers. Third, ignoring combustible dust requirements. Fourth, allowing dust to accumulate on rafters, lights, and beams. 5th, not grounding ductwork when handling synthetic fibers. 6th, using open cutting or trimming stations without hoods. These mistakes reduce efficiency and significantly increase fire hazards. What I always do on textile dust projects. My engineering approach includes, first, identifying the fiber type, natural, synthetic, or blended. Second, measuring dust load and particle size distribution. Third, designing high-velocity ductwork to keep fibers moving. Fourth, selecting collectors that can handle sticky or tangled lint. Fifth, including explosion protection for combustible materials. Sixth, using anti-static media when synthetics are present. Seventh, designing fully enclosed capture hoods with easy access. This ensures safe, reliable, and compliant operation. Textile dust may look soft and gentle, but it is lightweight, airborne, fibrous, combustible, and capable of traveling everywhere in a facility. With proper airflow, high-efficiency filtration, and well-designed hoods, it can be controlled safely and effectively. I am Michael Klepik. Protect your lungs, protect your equipment, and remember, textile dust belongs in the collector, not floating through the air like confetti at a fashion show. See you in the next video.